Hello and welcome to the Team 42 presentation for the Engineering Challenges project. Uganda is an East African country, ranked 161st on the Human Index Development in 2014. When the country not having a very good health system, it is no surprise that a contagious disease like tuberculosis will be hard to cope with. In 2017, the mortality rate of this disease in Uganda was of 2.6%. And even if 89% of children are vaccinated in the country, the fact that there is a high HIV infections and an undeveloped health system allows the number of people contaminated by the disease to increase. To help its population, the country needs a high amount of BCG vaccine, which is our task for this project. The project was divided into three main parts. Firstly, we needed to propose a location where to build the vaccine plant that was conformant with the requests of the Ugandan government. Once a location was found, it was necessary to model a hydroelectric dam to supply power to the plant. And the third and final part of the project required designing pylons that could transport the power from the dam to the plant's location.
The following list represents the criteria that the location of the plant should have, ordered from most important to least important. First, our priority was the given conditions set by the government, a water supply needed for the hydro plant and the operation of the plant, a power supply connecting the vaccine plant and the hydro plant to the main grid, and a region with high potential of economic development, as this is the key government project aiming to accelerate the national economy. Second, we considered the conditions for structural safety of the site itself, making sure the plant was not built on soils with severe issues such as liquefaction, and avoiding any earthquake fault lines. Finally, we considered conditions which would benefit the construction and the operation of the plant. Being located close to health facilities was important as it would provide the needed healthcare in the construction sites, and also help the distribution and the development of the vaccine itself. To aid with the distribution of the vaccine, access to transportation such as main roads, railways, and airports was next to our agenda. Population of the area and educational institutions are also needed to be considered, as we require workers for the construction and high-level workers for the plants. A large population will mean cheap labor will be accessible, and educational institutions means high-skilled labor will also be available. Waste disposal comes last, but still of major importance, as a vaccine plant will produce several types of waste, including chemical waste that has to be treated specially.
Out of the many locations in Uganda, we shortlisted Nyarava, Bwera, and Jinja as all three met most of the criteria. Comparing the three locations, we could decipher that Jinja was a better location out of the three, as it had more optimal conditions, such as having better transport, electricity, and water accessibility. Jinja is very well connected via several forms of transport. This means it allows for efficient distribution of vaccines. The Victoria Nile provides an adequate water supply and supports a hydroelectric plant of 200 megawatts. Furthermore, the developed infrastructure, including educational institutions with a large population, promises a quality workforce. Although the center of Jinja, where our site is located, it has less economic potential, the outskirts seem to have strong potential for economic development. Despite our proposal of Jinja, the Ugandan government has decided to choose Mbarara for its location. The main reason for this selection is that the city has most potential for economic development. We can see from the map on the right that surrounding Mbarara are many low-density populated areas that can grow and develop with the implementation of the vaccine plant. Mbarara also has good transport links by road and air that can allow supplies and products to travel efficiently. Now that a site has been chosen, we need to design two structures for the plant: a hydroelectric plant providing a minimum of 2 megawatts of electricity, and a pylon which will carry the two 10 kilonewtons of electric cables.
To supply the vaccine plant with electricity, we were tasked with designing a hydroelectric plant in the river Ntugwe. The dam has to have minimum power output of 2 megawatts, maximum elevation of 1,290 meters, and a minimum outflow of 3 meters per second. We found that during the summer period, the flow rate in the river will be very low. That means that during this time, the power output will also be very low. This is crucial to locate the dam in a position where the volume of the reservoir is as big as possible so that the low impact input affects less. From the power output equation, we can see that the height of the dam directly inputs the power output. Hence, we decided our dam to be located in an area where the lowest elevation was 1,230 meters, allowing for the maximum height of 60 meters. Next is the problem of fluctuating flow rate per season. We decided that our volume should be as large as possible. This would allow the fluctuation of flow rate to affect our power output less. As the location of our dam has been set, we decided our dam should be an embankment dam, as the soil underneath was soft. So our dam would be an embankment with a maximum head of 60 meters. From here, we start making a numerical model for our power output. Now we have our dam, we can figure out the flooded volume. From the highlighter model flooded area, we will be able to model these into 4 different trapezoids as shown. By adding these together, we were able to get the flooded volume of 4.3 times 10 to the power of 7 meters cubed. From this value, we were able to create a numerical model of our dam's power output by calculating the varying volume and the actual height corresponding to the actual volume.
From the numerical model of our dam, we managed to find the function for the relationship between the diameter of the penstock and the maximum and minimum power outputs of the dam. We can see that the shorter diameters have lower minimum and maximum outputs, as a small amount of water flows through the penstock. For the longer diameter, the maximum power was very high, but the minimum power was lower than the minimum value. This is because more water flows through the wider diameter and the reservoir empties faster, leaving too little water in the summer. Looking at the graph, we decided to choose a value near the point where the minimum power curve intersects 2 megawatts, the specified minimum output. At this point, the power output during the rest of the year is the highest amongst the range of diameters, with minimum outputs of 2 megawatts. The optimal power for the diameter was 0.58 meters. Also, for a penstock length, as the bottom of our dam is flat, we used a 20-meter length with no elevation, so that we can allow for the water to pass from the deepest point in the reservoir. We can also see that the output flow of the dam varies significantly, but is always greater than 3 meters per second, as set in the original requirement. All penstocks with diameters above 0.35 meter sizes were suitable from this point of view. Furthermore, the volume of water in the reservoir is always high, even in the summer, due to the size of the penstock and the volume of reservoir. More water is allowed to be stored in the reservoir throughout the year. As we mentioned before, the specific penstock size allows for a steady and high power output throughout the year, and the power output above the minimum value in the summer. This is reflected in this graph, where the power output is constantly 4.27 megawatts, except for the beginning, where the dam is filling up, and a dip in the summer, where the power reaches a minimum value of just above 2 megawatts. From our numerical model, we decided that the best turbine is Francis. We can see from the turbine selection diagram that our values for head and flow rate of the river fit in the region for Francis and Kaplan. In fact, Pelton and Turgo are usually used for higher heads compared to ours. Kaplan is typically used for lower heads and greater flow rates compared to the dam we have designed, which makes Francis better suited for the head and flow of our dam specifically. We have also calculated the relative discharge to be between 70 and 90%, meaning that the efficiency of the Francis turbine is 90%, as we can see from the diagram, a very high value. This slide summarizes our final dam design proposal. As already mentioned, we have tested it in our numerical model, and we believe that this design will produce the maximum amount of power throughout the entire year, whilst meeting all the requirements set by the government.
In order to transmit electricity from the hydroelectric power station to the Mbarara, we have to design a truss-shaped pylon composed of hollow members. It has to be original so that Uganda can stand out internationally, built with the least amount of materials to cut costs, withstand 2 loads of 10 kilonewtons, easy to assemble for workers, have members with stress below 200 kilonewtons and internal compressive forces below 2/3 of the buckling load. After considering the limits in stress and internal force of each member, we can decide the diameter and thickness of the hollow members as well. We have designed 3 pylons in total. For the first one, it's symmetric and is made from 13 members. There are 4 sections of diameters, which are 20 millimeters, 40 millimeters, 70 millimeters, and 130 millimeters, and 2 sections of thickness, which are 5 millimeters and 10 millimeters. The second pylon is a more conventional take on the first design. It consists of 15 members, which are all similar in length. It promises to be very easy to assemble, but the design is too standard to stand out. The third pylon is unique in its shape, resembling the lightning bolt. It's made from 9 members having a thickness of 5 millimeters, except for the one that has 10 millimeters, diameter varying between 20 meters and 140 meters, and length varying between 4 meters and 40.4 meters. We first did a hand calculation of all the axial forces in our top pylons, which then we checked by using the software Oasis GSA. This was to better understand the members and figure out any issues before they became substantial. From the acquired axial forces, we needed to find the adequate cross-sectional area so that the pylon will be safe under both stress and buckling. Hence, we used the equation stress equals internal axial force over cross-sectional area and make sure the stress is below 200 kilonewtons. And for the members in compression, we ensure that the compressive forces of members should not exceed 2/3 of a buckling load. We can calculate buckling load by the equation buckling load equals force times elastic modulus times second moment of area over length squared. From this, we were able to find the adequate cross-sections for our members and pylon. Eventually, we have chosen the third design because it's unconventional and original in its shape, and is only composed of 9 members, so the assembly is easier. Moreover, after the analysis of pylon on stress and buckling load, it's found that no member is overloaded and the weight is well distributed. The stress on each member does not exceed the limit of 200 kilonewtons, and the compressive forces on members do not exceed 2/3 of buckling load as well. To create a working real-life model of the pylon, we have to transfer the pylon from 2D to 3D. The diameter and the thickness of the members were changed to ensure the stress and compressive forces on members do not exceed the limits stated in criteria. The pylon is then analyzed under 2 extreme cases: wind loading of 25 kilonewtons per meter and the loss of a roller support. Under wind load, the first thing we can see is that there are obvious movements in the top left nodes, and the roller support on the right in the direction of the wind. It can be shown that the reason for the movement in the right roller is due to the middle section shifting to the direction of the wind as well. Furthermore, from the right graph, it can be seen that compressive forces in member 3 and 6 exceed the buckling resistance, so they buckle and this causes a chain of buckling within the pylon so it'll fail eventually. When the roller support is removed, it can be seen that the pylon goes through major deformation and fails to the side where the support is empty. Also, there is a large deformation on the bottom right roller support as well. We believe it's deformed to accommodate the rotation of pylon due to the loss of a roller support. From the stress graph on the left, you can see that the stress of pylon with only 3 supports is relatively larger than the one with the 4 supports. From the buckling resistance graph on the right, you can see that after the roller support is removed, the compressive forces in the members exceed the buckling resistance, so the pylon buckles and fails. We found although our design worked very well under standard conditions, it failed under extreme conditions. This was as although we had designed specifically to resist the weight of the pylon, we did not calculate how it would behave under extreme conditions, such as wind or loss of support. By designing the pylons to withstand these loads, we should be able to get a working design where it does not fail. In conclusion, during this module, we have designed 3 main components to the proposed vaccine plant: the site where the vaccine will be produced, the hydroelectric power plant to supply electricity, and the pylons which will then carry the electricity to the plant. We have learned from an engineer's perspective how to submit design proposals, to think about the priorities of a task, what conditions to consider for a task, and to collaborate with different fields of engineering. Thank you for listening.